Welcome back. We're now in submodule 3.5, which discusses plotting functions. We'll look at some basic techniques for this, as well as introduce notions of symmetry, which can become very helpful in plotting functions. So let's just recall that we can plot functions in the Cartesian plane, and that's very useful for understanding the kinds of relationships it defines. The typical and naive way to do this is to compute many pairs of the function's input and output, putting these into the Cartesian plane as dots, and trying to draw some sort of curve that fits the dots in a good way. Now, this is perfectly fine if you have lots of time. But if you know sort of roughly how certain functions behave, then you might not need to plot very many points, in fact, perhaps none at all. So there's sort of a benefit to understanding the basic plots. You save yourself a lot of time in sort of looking at different dots on the Cartesian plane and trying to fit a curve through them. So let's just look at a few examples of where I think it's helpful to have a basic picture in your mind. Let's take f of x to be equal to x plus 1 squared. So I think in this case it's better to leave it factored because I know what the shape of a quadratic is. All I need is a little bit of extra information here to help me plot this very quickly. So let's plug in a couple points. So I plug in 0, I get 1. So this point's on there. If I plug in 1, I get 4. So a point like there. And if I plug in minus 1, I get 0. And let's just do one more. Minus 2, I get 1. So I can sort of see the shape of a parabola if I'm able to recognize that it should sort of look like a smoothed V. So the plot is something like this. So this is why I say it's helpful if you know the basic picture of a quadratic polynomial. It's going to make sort of a bowl-shaped, or what I call a smoothed V, either upwards or downwards. So choosing a few well-chosen points can make plotting this very fast and efficient. Let's look at another example that I think is easy to plot. Let's take, for example, f of x is just a linear function, 3x plus 2. Now I think in this case it's not even necessary to pick points to plot. All the information I need is contained in the function statement. I know that the slope of this line is given by 3, and the y-intercept, which I guess you could think of as a point on the line, is equal to 2. So with those in mind, I get the following sketch. Make some hash marks. Okay, so I know that I hit this point here, and my slope is 3. So the sketch is, it should be somehow straighter than this, but the sketch is more or less like this. Okay, and for this I didn't need to really even plot points. Just use the slope and the y-intercept. So let's look at one more sort of trickier example. Let's take f of x equals square root of x plus 3. So in this case, I think it's helpful to have a picture of what just regular old square root of x looks like. So we'll draw this in purple. So we recall that it looks something like this. So what is the difference between this plot and the one I want? Well, the only difference is I add 3 to the example that I would like. So how does that impact my plot? We'll get to this in sort of a very definitive way in the next section, but I think it's sort of clear what's going to happen if I pick a few points and make a table. If I plug in 0, I'm going to get 3. If I plug in 1, I'm going to get 4. If I plug in 4, I'm going to get 5. So the picture is very similar except shifted up by 3. We'll draw the plot like this. So at 0, I have the value 3. At 1, I have the value 4. And at 1, 2, 3, 4, I have the value 5. So the picture is something like this. And I was able to get this very quickly because I already had some idea of what the square root function looked like. So this is among the kind of handful of examples I would really recommend keeping stored in your memory. Lines, parabolas, square root, e to the x, and log of x. If you can have these sort of stored in memory, it'll be very easy to plot them quickly and identify their plots on the CLEP exam.